Welcome to this explainer. Today, we're tackling one of the deepest, most mind-bending questions humanity has ever asked. What actually existed before the Big Bang? And to guide us through this, we're doing something a little different. We are joining our animated comic strip heroes, the wildly enthusiastic Captain Quantum and the endlessly witty Dr. Gravity. They are currently firing up their time ship for a cosmic voyage, and they're taking us along for the ride.
So let's dive right in, because instead of starting at a beginning we don't really understand, we're going to hit rewind. We're taking the universe exactly as it exists right now, with all its sprawling galaxies, stars, and planets, and we are just running the clock backward. It is literally the ultimate reverse road trip to the very edge of known physics.
Right out of the gate, Dr. Gravity needs to bust a massive myth about our universe's origin. You know the picture: a dark, empty void, absolute nothingness, and then bam, a bomb goes off, blasting matter outward. Yeah, no, the reality is completely different. There was no pre-existing dark void just waiting around for an explosion. The Big Bang was the condition of space itself expanding, everywhere, all at once. It wasn't an explosion in space, it was the explosion of space. That is an absolutely crucial distinction.
To really picture this, Captain Quantum loves to use the classic raisin bread analogy. Think about baking a loaf of raisin bread in the oven. As that dough rises and expands, every single raisin moves farther away from every other raisin, right? But the raisins aren't actually flying through the dough. The dough between them is growing. In our universe, galaxies are the raisins, and space is the dough. So, as our time ship throws it in reverse, that dough is essentially unbaking. The actual space between everything is shrinking.
Now, before we hit light speed, here's a fun little aside. The term Big Bang, it was actually coined back in 1949 by a British astronomer named Fred Hoyle. And ironically enough, Hoyle absolutely hated the theory. He was heavily in favor of a model where the universe had no beginning. On a BBC radio broadcast, he literally called it this Big Bang idea as a snarky insult, but the catchy name stuck. And today, the entire framework of modern cosmology carries a name that was invented as a put-down.
Okay, Captain Quantum is engaging the jump drive. We're mapping out our reverse chronological pit stops here. We're jumping from the present day back to 380,000 years after the beginning, then to a mind-bending 1 microsecond, and finally, all the way back to time zero. Buckle up.
But hey, how do we actually know any of this is real? Well, picture this. It's 1964. Arno Penzias and Robert Wilson are calibrating a massive horn antenna at Bell Labs, but they keep picking up this maddening, persistent static. They check everything, they even find a flock of pigeons nesting inside, evict them, and meticulously scrub out all the, pigeon poop, thinking that was the interference. But the noise was still there. Turns out they had accidentally discovered the cosmic microwave background, the ancient cooled-down afterglow of the Big Bang itself. Talk about a happy accident.
And that ancient microwave afterglow? It fills the entire universe today. Its temperature has been measured with astonishing precision. It is exactly 2.725 Kelvin, just a tiny fraction above absolute zero. To put that into perspective, this specific number is the frozen echo of the universe's fiery creation, stretched out and cooled over 13.8 billion years of expansion. It is quite literally the oldest light that will ever wash over you.
All right, Captain Quantum just announced our time ship has successfully jumped to our first major stop in the deep past, 380,000 years after the beginning. And it's getting a bit toasty out there. Because we're rewinding time, the universe is shrinking and heating up, and we're currently sitting in a blistering 3,000 Kelvin environment. Basically, we've just crashed the recombination party.
Dr. Gravity's quick to point out a pretty hilarious quirk of scientific naming here. Recombination is the epoch when 3 electrons finally cool down just enough to get snagged by atomic nuclei, forming stable atoms, the very same atoms in your body right now. But, as the good doctor notes, recombination is a terrible name. These particles hadn't ever been combined before in the entire history of the universe. They were combining for the very first time. But hey, science loves a legacy term, so we're stuck with it.
Now, because we're traveling backward, we're watching this process in reverse. As we slip into the era before 380,000 years, those stable atoms are ripped apart again by the intense heat. That perfectly clear, transparent universe we're used to, it suddenly fills with this completely opaque, glowing plasma fog. Light literally can't travel freely anymore. Every single photon is trapped, bouncing endlessly in a chaotic pinball game of free electrons. It is blindingly bright, but you can't see a thing.
Time to hit the throttle. We are jumping way further back. We are now at just 1/1,000,000th of a second, 1 microsecond after the beginning. The temperature? An incomprehensible 1 trillion Kelvin. Welcome to the Quark Soup Kitchen.
Check out this recipe for a quark-gluon plasma. At 1 trillion Kelvin, conditions are so extreme that protons and neutrons can't even hold themselves together. They literally melt down into a free-roaming, boiling soup of quarks and gluons. You've got particles and antiparticles furiously popping into existence, immediately annihilating each other in a frantic cosmic dance. This ultra-hot soup is the fundamental raw material for everything you've ever interacted with. It's a state of matter we've only barely managed to recreate for fleeting fractions of a second in our biggest particle accelerators on Earth. Captain Quantum is literally yelling over the time ship's alarms right now. We have hit 10 to the power of -36 seconds. We are in the era of cosmic inflation. This is an unimaginably brief window, deep in the absolute smallest fractions of a second, where the universe decided to break absolutely every speed limit in existence.
Dr. Gravity calmly steps in here to explain why this violent exponential stretching is so incredibly vital to cosmologists. Basically, inflation fixes everything. It explains why the microwave background is the exact same temperature everywhere, because the whole universe was in contact before being violently ripped apart. It explains why the geometry of space is flat. It essentially pulled the fabric of space so fast and so hard that it ironed out all the wrinkles. And it perfectly dilutes these hypothetical exotic particles called magnetic monopoles, spreading them so incredibly thin we can never find one.
And now we've reached the end of the line. Time zero, the final barrier. Our time ship's dashboard is just flashing red warning lights everywhere because standard physics is undergoing a complete meltdown. We are entering the quantum boundary, where our verified scientific models officially give way to the ultimate unknown.
So here's the crucial point about the singularity. When most people hear that word, they picture a tiny physical dot of infinite density just waiting to explode. But that's not what it means to a physicist. The singularity is really just a mathematical warning sign. It's what happens when Einstein's equations of general relativity start spitting out infinities. It's essentially a math error code. It's telling us our theory has completely broken down because we don't have a unified theory of quantum gravity yet. It's not necessarily a real physical object, it's a hard limit on our current knowledge.
So how do theoretical physicists handle an error code like that? Well, Captain Quantum and Dr. Gravity are consulting the Hartle-Hawking no-boundary model. It's a truly beautiful idea. It suggests that as you squeeze back into this incredibly hot, super-dense state, time doesn't just hit a sharp singular starting point. Instead, time itself transforms. It gradually becomes more like a spatial dimension. It naturally rounds off, like a sphere. It becomes the south pole of time.
And here is Dr. Gravity's ultimate punchline. If this Hartle-Hawking model is right, then asking what came before the Big Bang is exactly like asking what is south of the South Pole. Think about it. It's a grammatically correct question, sure, but it carries absolutely zero physical meaning. You literally can't walk further south than the South Pole, and you just can't go further back in time than the rounded-off origin of the universe.
But wait, didn't the universe come from nothing? Well, Captain Quantum points out that nothing is a notoriously slippery word in physics. There are really 3 shades of it. First, you have empty space, which isn't nothing at all. It's a fabric packed with fields. Then you have the quantum vacuum, which is seething with virtual particles popping in and out of existence. When physicists say the universe popped out of nothing, they usually mean that highly active quantum vacuum. Finally, there's absolute nothing. No space, no time, no laws of physics whatsoever. That is a philosophically debated concept that we don't even know is logically possible.
Plus, there are other wild ideas on the frontier. For instance, alternative frameworks like loop quantum gravity suggest our universe might not have even had an absolute beginning at all. Instead, we might be living in a bouncing cosmology. In this view, our Big Bang was really just a bounce. It was triggered when a previously contracting universe got too dense and just rebounded. Which means the cosmos might just expand, contract, and bounce in an endless, infinite cycle.
Which leaves us with this final, provocative question to ponder. Is absolute nothing even a logically coherent concept? Can there truly be an absence of all laws, all space, and all time? As we bring Captain Quantum and Dr. Gravity safely back to the present day, we have to admit the frontier of cosmology is still actively moving. The Big Bang model perfectly describes an expanding, cooling universe, but that ultimate starting spark remains a beautifully open question. Thank you for joining this explainer, and stay eager to explore whatever secrets our cosmos reveals next.